Okay, continuing with our examples of putting voltages across resistors, capacitors and inductors, let's look at an example of a ramp voltage now put across a capacitor. So the ramp voltage, 10 volts per second, means that the voltage is increasing at the rate of 10 volts per second. And for this particular example, we're assuming it's going to carry on rising at that rate indefinitely. Obviously, when you come to your assignment, we can't have the voltage increasing indefinitely, so you're going to reach a limiting value, at which point the voltage will become steady. And that will obviously have an effect on the circuit, which you'll need to consider. So, we're going to use Ohm's law to analyze the current in this circuit. Current is voltage over resistance, E for the voltage, Z for the impedance of the circuit. We just need to transform both of those into using Laplace transforms on page 5 and then work through the algebra. You can pause this recording at various stages and see if you can carry it on. So write down what the Laplace transforms are for the voltage and for the total impedance in the circuit. So you should have that E in S space. Now will be 10 over S squared, because it's the ramp voltage input, and the impedance, Z, for a resistor, that stays as it is, and for a capacitor, it becomes 1 over 0.01 S. Now we put these two into Ohm's law, and start to try and use algebra to tidy it up. So, putting this circuit into Ohm's law, we get IS equals E over ZS. Transform those, put those transforms in and see how you get on with the algebra. I'll pause every now and then and you can see if you can carry on from there. So first step, so we have 10 over S squared divided by 20 plus 1 over 0.01 S. Dividing by 20 plus 1 over 0.01 S is the same as multiplying by 1 over that. Remember, if I do say A divided by B, as we talked about before, this is equivalent to A times 1 over B. So we'll end up with IS equals 10 over S squared 20 plus 1 over 0.01 S, effectively. Now multiply out the brackets at the bottom and then try tidying up from there. IS equals 10 over 20 S squared plus 1 over 0.01 and S at the top. S over 0.1 times S, effectively. What might you do about this part here? 1 over 0.01. Well, we can multiply top and bottom of that fraction by 100 to get rid of the 0.01. Plus 100S. And that makes things a bit more straightforward. What I might do now, divide top and bottom by 10, because 10 goes into each of the three terms, and this will give me 1 over 2S squared plus 10S. Now, bring an S outside at the bottom, 1 over S into 2S plus 10. And now we're going to use partial fractions to split this into its two components. So have a go at that. So we rewrite this fraction 1 over s into 2s plus 10 as something over s, which is one of the factors, plus b over the other factor, 2s plus 10. Next step is to make the denominators both sides the same. So 1 over s into 2s plus 10 equals a times 2s plus 10 plus bs over s into 2s plus 10. This idea of cross multiplying. See if you can carry on from there. What we do is equate numerators. Because the denominators are the same, the numerators are the same. So 1 equals a 2s plus 10 plus bs. Then we multiply out the brackets and collect terms involving s and the constants. So see if you can carry on from there. 1 equals 2as plus 10a plus bs. Collect factorising the s part, so we get 2a plus b s plus 10a equals 1. Now we equate coefficients. The coefficients of s and the constants, but they must be the same on the left-hand side and the right-hand side. And that would allow us to find out what the values of a and b are. So have a go. So we have that the constant on the right-hand side, 10a, must equal 1, which is the constant on the left-hand side. And we also get that the coefficient of s, which is 2a plus b, on the left-hand side, must equal the coefficient of s on the left-hand side, rather, must equal the coefficient of s, which is 0. So 2a plus b equals 0. And from those two, we can straight away say that a equals 0.1, dividing both sides by 10. Putting this value into the second equation, we get that b equals minus 0.2. Just check that that's true. Now we can put these back in to the original equation at the top and say therefore that is equals a, which is 0.1 over s, minus 0.2 over 2s plus 10. And now we've got to try and get those two transforms to look at our table of transforms and see if we can transform them back. So see if you can do that next step. Well, the first one can be transformed directly because there's one in the table that looks just like that. But the second one, if we notice in the transform table, s in the bottom is always on its own, so we need to get just s on there, so divide by 2. If we divide by 2, we've got to divide every term, top and bottom, by 2. So we get minus 0.1 over s plus 5. Now we can transform those back. See if you can do that from the table. And we should get that it equals 0.1 minus 0.1 e to the minus 5t. We can make that look familiar by factorising and taking 0.1 outside the bracket, which is a common thing to do because that will leave us 1 minus e to the minus 5t inside the bracket, and hopefully you recognize that as an exponential growth to a limit. And what is that limit? The limit is this number outside the bracket. So it's going to grow until the current reaches a steady value of 0.1 amps. But we can put that into autograph and check what the curve looks like. So if you'd like to fire autograph up and try putting that in. So remember, autograph only uses y and x as a variable, so the dependent variable, which in this case is the current, is going to have to be y equals 0.1 open bracket 1 minus e to the power, which is the hat symbol above the 6, and then I always put everything that follows in the bracket so it knows that it's to the power of all that follows, minus 5x. Close the bracket and then close the bracket again and hit equals, or hit OK rather, and we get the curve. See from the curve that everything's going on right down here on the y-axis, so to focus in on that, zoom in on the y-axis, and you should expand that curve upwards, and we can see it's growing to a limit of 0.1. We're only interested in what happens after t equals 0, so let's shift it to the right. We could do with zooming in on the x-axis and seeing what's going on. Just this is the part of the curve we're interested in, so let's zoom on the x-axis again. Maybe zoom in again on the y-axis and then drag it about, and that tells us how the current is going to behave in this particular circuit. And we can see from it that it reached a steady value of 0.1 amps, but we can now tell how long that's going to take. It looks as if it takes around about a second for this current to reach this steady value. And you can see I put this curve in the notes, if you've got the notes there. Don't forget, we're expecting that the voltage is 10 volts per second, and that's going on indefinitely. So in other words, you're going to reach this steady current of 0.1 amps, and then you have a steady current of 0.1 amps so long as the voltage continues to rise at 10 volts per second. Obviously, it's not going to be able to rise at that rate for long. Okay, how about you try this one? We've got a ramp voltage of 2 volts per second across a resistor and a capacitor in series. The solution you should find is below, so that's what you should get at the end, and I've plotted it. And so you can estimate if you plot that in autograph, how long it will take for this circuit to reach a steady value. In other words, you're analysing the transient period.